Hey everybody. So I am back with actually a quick correction on my last video. So last time, I guess I'll go over this real quick. I wrote two functions, tangent and normal, in order to calculate the tangent and normal vectors, which are going to be used for the Frene serie, and they followed this formula. And while the math I did was correct, I didn't really create it as one function using closure. And so that's what I'm going to try to accomplish in this episode. So without any further ado, let me go ahead and I'll leave all this on the screen, but let me go create a new function. And we're going to define this function as Frene serie, and we want to pass into this Frene serie function just some random function. I guess in this case we want it to be the curve, but I'll just call it f just for simplicity. And then, of course, from this, we want to return a function for the tangent and a function for the normal. And I'll define those as I go. So I guess, I'll just go ahead and define them right now. Define tangent in terms of t, in terms of the time, right? And that is going to return just something. I will just leave it blank for now. And then we're going to define normal in terms of t, and that is going to be returning something that we calculate. So yeah, just to be clear, this function Frene serie is actually returning me functions of tangent and the normal vectors. So yeah, well, how did we go about doing this before? Well, we took the Jacobian of the curve, and then we divided the Jacobian of the curve by the magnitude using this Lin algebra norm function. And that gave us the tangent, or at least the like this function. And then we got the normal by taking the magnitude, well, not the magnitude, by taking the Jacobian and magnitude of this tangent function, right? The vector tangent to the curve, n is the normal unit vector, b is the binomial unit vector, which I will get to in a little while. But yeah, anyway. So what do I need to continue doing on this curve, right? Well, first off, I'm going to start out by taking the change in the function that's given over time, and that's going, of course, to be equal to Jax's, or we're just going to use Jax's Jacobian function. So Jacobian, I spelled it wrong, Jacobian, of f, right? And then, so that is the df over dt, but we need to divide that by the change in arc length over time. And as I discussed before, the way you get this change in arc length over time is by taking the ds over dt. The way you get that is by taking the Lin algebra norm of the vector. So I'll go ahead and define that as a function. So define ds over dt in terms of t, and then that will just return the function it'll return Jax numpy's Lin alg norm, which is the magnitude of the vector, and so it is the magnitude of df over dt in terms of t. So that should be good there. And now we want to define this tangent as something. So I have a few options here. Actually, I don't really have options. I don't know why I phrased it that way. I need to take the change in f, so the change in this function over time, or the Jacobian of the initial function I passed, and divide it by this ds over dt, right? And we're doing that because the change in times will cancel out, and we will be left with just the change in tangent over change in s. So yeah, I'll go ahead and put a space in between all that. And then I just want to give it the ds over dt, so the change in arc length over time, as opposed to t, as opposed to t. So then for this normal function, I need to take, once again, going up here, normal function, I need to take the Jacobian of the tangent function and then divide it by the magnitude of the Jacobian of the tangent function. So let me go ahead and say that I always do this. The big T, so the Jacobian of the tangent function over time is going to be Jack's Jacobian. I spelled Jack's wrong because, yes, Jax's Jacobian function of tangent. So I will copy and paste tangent. And yeah, that should be correct, right? So then I will just take this change in tangent over time at the point t, and then divide that by what we started with up here. So this change in arc length over time at a certain point t. So I'll go ahead and run that, and won't get any math errors, so that's good. So let's go ahead and try to test this out. So I'll just maybe say that, yeah, the tangent function and the normal function are equal to, if I could spell, frene serie of f. And f, of course, we want to be curve, which I already ran this bunk of code up here, which runs this function. So this is the curve function. And let's see what I get as a result of that. I already ran that block, and I didn't get anything. So let's try to take the tangent at a certain time. Let's say at 0, right? Because I believe that's what I did up here. Well, no, okay. What I did up here was I took the normal to the curve. So let me maybe just try to test the same thing. I'll just define that as normal, and I get an error. But the good news is I was expecting that error. Because, look at this, type error. Curve wants 3 arguments. It wants an R argument and an MZ argument. Well, I don't really want to go ahead and define it that way because I just want it to be in terms of t, right? I just want to take the derivative in terms of t. So I will go ahead and create a new function for curve. So I'll go ahead and call this R underscore MZ curve. And so I will just totally redefine this old function and copy it and run it just to get this all saved up here. Then I'm just going to copy this down and probably put it in a new cell, put it in this cell right here. And I'll just call that curve again. And instead of asking for R and MZ as values, I'm just going to go inside of curve and define R as 3 and the slope in the Z direction as 0.4. R is the radius of the big circle, by the way. I always want to say the actual names of variables and not just like R and Z. But go ahead and run that. And now, I believe if I try to get the normal, I should get, let's see, we get this negative 3.2. It's a little bit different than what we got up here, but I believe that's because I did the math incorrectly up here. So let's think about this for a second. Maybe let's go ahead and say tangent. So if I could spell it correctly, Tangent. So tangent at point 0. So that's saying that when t is equal to 0, the tangent to this curve right here, I'll go ahead and run that again because I need it. So it's saying that when t is equal to 0, that's what this is saying, the x value, or the derivative of the x value, is going to be 0. The derivative of the y value, well, actually, it's not exactly saying that because it's dividing by the magnitude. So that dividing by the magnitude is what I didn't do up here. So that's why I shouldn't really be looking at this. So if you look at just like the numbers, well, what is the change in the x direction up here? Okay, I just broke something on my computer. I don't know what. But, yeah, so this is when t equals 0. What is the change in the x? Well, all the change is in the y direction, right? All the change is in this y direction. So there should be 0 in the x. And then the numbers aren't going to be exactly correct, but you see in the y direction, it's saying there's 1. So what should the change in the y direction be? Well, it should be pretty close to 1. It's divided by the magnitude, so that's going to make it so it's not very intuitive to see the normal or the tangent, but that's kind of what we would expect. And then the change in the z is going to be just this slope value divided by the magnitude of the slope value. So if we were to go and say take tangent at 4, we would see the exact same slope value, which indicates that what I've done is correct. And so with that, I'll go ahead and stop this recording, and then I will follow up by doing part 3, explaining a code function that calculates a surface point at a distance at a certain radius from the central helix for some angle between n and the cross product of t times n. Why is it necessary to use the cross product? Hint, it's because it creates a plane we can use. But I will get to that in the next episode, and I'm looking forward to that, but I will see you then. Yeah, I shouldn't even wave. Yeah.